A faint, cold glow fills the entire cosmos. This is the cosmic microwave background, an ancient light carrying the secrets of our universe's birth. By the end of this journey, you will understand how this primal echo reshapes everything we know about reality. We will uncover why this radiation holds a map to the first structures, and what its subtle imperfections reveal about the void before time. How does it feel to look directly into the cradle of creation? That first flash of light was the universe's primal scream, a single instant of transparency frozen in time. For nearly 400,000 years, everything was a searing, chaotic fog. Electrons and protons, all electrically charged, were constantly scattering the very first photons, trapping light in a relentless dance. The cosmos was a brilliant, impenetrable soup. But then, expansion worked its magic, cooling the dense plasma just enough. In an event cosmologists call recombination, electrons finally slowed down and were captured by protons, forming the very first neutral hydrogen atoms. Think of it like a dense, roaring crowd suddenly parting. The charged particles that had been blocking the light were now bound up in stable, neutral atoms. And with the road suddenly clear, that trapped light burst free. Every corner of the universe flooded with this primordial glow. That initial flash of visible light has been traveling for over 13 billion years, stretched by the expanding fabric of space itself into the faint microwave whisper we can now detect with our telescopes. It is not just a distant echo. It is the oldest photograph in existence, a baby picture of the cosmos, taken when it was a mere 380,000 years old. And within that image, every subtle variation in temperature, every tiny hot spot and cold spot, is a message from the dawn of time waiting to be decoded. That baby picture of the cosmos, the oldest light in the universe, sat quietly in the background for billions of years, completely unknown to us. Its discovery was not the result of a grand, targeted search, but a story of brilliant minds solving a very different, very earthly puzzle. In 1965, two radio astronomers, Penzias and Robert Wilson, were working with a massive, ultrasensitive horn antenna at Bell Labs in New Jersey. Their goal was to study radio waves from our own galaxy, but they were plagued by a persistent, maddening noise. It was a faint, constant hiss that came from every direction in the sky, day and night, and it just would not go away. They checked everything. They thought it might be radio interference from nearby New York City. They meticulously scrubbed the giant antenna, even cleaning out a sticky residue left by pigeons that had nested inside, which they jokingly referred to as a white dielectric material. Yet the hiss remained. It was an unshakable ghost in the machine. After months of frustration and systematically eliminating every possible source of error, they were forced to confront a staggering possibility. The noise was not a flaw in their equipment. It was not from Earth, and it was not even from our galaxy. This faint, uniform signal was coming from the universe itself. They had accidentally stumbled upon the cosmic microwave background radiation, the cooled remnant of the universe's fiery birth. At the very same time, just a short distance away at Princeton University, a team of physicists led by Robert Dick had been actively building a detector to find this exact signal, a prediction of the Big Bang theory that had been proposed years earlier. When Penzias and Wilson called them to discuss their mysterious noise, the Princeton team immediately understood what they had found. This chance encounter, this beautiful accident, provided the first direct, overwhelming evidence for the Big Bang, transforming our understanding of the cosmos from a philosophical debate into a rigorous science. For discovering the echo of creation itself, Penzias and Wilson were awarded the Nobel Prize in Physics. It was a humble beginning, born from troubleshooting a faulty antenna, that opened our ears to the faint whisper of the universe's first moment. That faint, universal hiss held a deeper secret, one that would not be revealed for decades. While Penzias and Wilson had found the cosmic afterglow, it appeared at first to be perfectly smooth, the same temperature in every direction. But the universe we see today is not smooth at all. It is a tapestry of galaxies, clusters, and vast cosmic voids. The question was, how did we get from such a uniform beginning to such a structured present? The answer was hidden in the subtlest of details. When scientists finally developed the tools to measure the cosmic microwave background with incredible precision, they discovered it is not perfectly uniform. It is imprinted with tiny temperature fluctuations, variations so minute they are like detecting a single warm grain of sand on a vast, cold beach. We call these anisotropies. These minute ripples, mere 100,000ths of a degree different from their surroundings, are the most important imperfections in the cosmos. They are the cosmic seeds from which everything grew. Each tiny hotspot, each slightly colder spot, corresponds to a region in the early universe that was a little denser or a little less dense than average. Think of it like a sheet of rubber that is almost perfectly flat, but has microscopic bumps and dimples. Over billions of years, gravity acts like a magnifying lens on these tiny imperfections. The slightly denser patches with just a little more gravitational pull began to attract more and more matter. Over cosmic time, these specks collapsed under their own weight, eventually forming the first stars, the galaxies, and the immense clusters we observe today. The less dense regions, meanwhile, evolved into the great cosmic voids, the empty stretches between the webs of galaxies. By creating exquisitely detailed maps of these fluctuations, missions like the Planck satellite have given us the original blueprint for the universe. This map is more than a baby picture. It is a genetic code, a frozen snapshot of the initial conditions that set the destiny for every structure that would ever form. Reading this ancient light tells us not only where we came from, but how the entire cosmic architecture was designed from the very first moments. This ancient light is more than a remnant. It is a messenger, carrying news from a time when the cosmos was 1,000 times smaller and hotter than it is today. Every single cosmic microwave background photon that reaches our telescopes has been on an epic journey, traveling for over 13 billion years almost completely undisturbed. To understand its message, we must first understand its origin in that crucial moment of transparency. Before this epoch, the universe was a brilliant, opaque fog. Charged particles, free electrons and protons, filled space, and any photon of light that tried to move would immediately collide with one and scatter in a new direction. Light was trapped, making the entire cosmos a glowing, impenetrable soup. But then came recombination. When electrons and protons combined to form the first neutral hydrogen atoms, the fog lifted in an instant. The charged obstacles were suddenly gone, and for the very first time, light could travel in a straight line. The universe became transparent. The photons that burst free in that single cosmic moment are the ones we see today as the CMB. They have been streaming through the expanding void ever since, their wavelengths stretched by the relentless growth of space itself, cooling from visible light into microwaves. When we point our detectors at this radiation, we are not just seeing an old glow. We are collecting direct snapshots of the universe at the tender age of only 380,000 years. These photons are pristine witnesses, and they carry encoded within them a perfect record of the density, temperature, and composition of the infant cosmos. Observing this light is the closest we will ever come to standing at the edge of time and gazing directly into the cradle of creation. That nearly uniform glow, the one Penzias and Wilson first heard as a faint hiss, is in fact a complex tapestry of temperature. When we create an all-sky map of the cosmic microwave background, it reveals a mottled pattern of hot and cold spots, a celestial leopard skin painted across the void. These variations are incredibly subtle, mere millionths of a degree, but they are not random noise. They follow a very specific, statistically predictable pattern, a pattern that was theorized long before we had the technology to see it. To understand what this pattern means, cosmologists use a powerful tool called a power spectrum. Think of it like listening to a complex chord of music and using a mathematical filter to separate out the individual notes. The power spectrum does exactly that for the CMB map. It breaks down the pattern of spots into its constituent waves, telling us how common spots of a certain size are across the sky. And the music this ancient light plays tells us fundamental truths about the cosmos. The most striking note in this cosmic symphony is the prevalence of spots that span about 1 degree across the sky. The size of these spots is not an accident. It is a direct reflection of the geometry of the universe itself. In a closed, spherical universe, light rays would bend toward each other, making spots appear larger. In an open, saddle-shaped universe, light rays would diverge, making spots look smaller. The fact that we see spots at this specific 1 degree scale is a monumental discovery. It tells us that, on the largest scales, the universe is flat. Not flat like a sheet of paper, but flat in its geometry, meaning that parallel light rays continue on paths that never converge or diverge. This finding of a flat universe was a critical pillar in building our modern cosmological model, confirming a key prediction of cosmic inflation. So, every time we look at that splotchy map of the infant cosmos, we are not just seeing a random collection of warm and cool patches. We are reading a cosmic code, a language of temperature written into the very fabric of space, and its first, most important word was flat. But how did those crucial imperfections, those tiny seeds for all structure, get there in the first place? The answer lies in a concept so profound it bridges the unimaginably small and the cosmically vast, cosmic inflation. Picture the universe in its very first instant, a trillionth of a trillionth of a trillionth of a second old. At that moment, a phenomenal burst of expansion occurred, stretching space itself faster than the speed of light. In that fleeting fraction of a second, the entire observable universe grew from a subatomic speck to something the size of a grapefruit. This explosive growth did something incredible. It took the faint, ghostly jitters of the quantum world, the temporary and random fluctuations in energy that constantly pop in and out of existence at the smallest scales, and it stretched them. It magnified these microscopic tremors, locking them into the very fabric of space-time and blowing them up to macroscopic proportions. Think of it like a tiny, microscopic wrinkle on the surface of a balloon. As you inflate the balloon to an immense size, that tiny, subatomic wrinkle becomes a vast, continent-sized ridge. In the exact same way, the quantum fluctuations from the universe's first moment were inflated into the slight density differences that would later appear as the hot and cold spots in the cosmic microwave background. This means the magnificent cosmic tapestry of galaxies and voids we see today, the very framework of our reality, can trace its origin back to random quantum fuzz. The pattern we read in the ancient light is a direct fossil, an imprint of those primordial quantum events. It is one of the most breathtaking ideas in all of science, that the entire observable universe, in all its splendor and complexity, grew from a subatomic seed. Those faint temperature ripples in the cosmic background are more than just a static image. They are a frozen symphony, the remnants of sound waves that crashed through the fiery plasma of the infant universe. To understand this, we must picture the cosmos before it became transparent, not as empty space, but as a dense, searing fluid. This fluid was a roiling sea of light or radiation and matter, mostly protons and electrons. In this primordial soup, two titanic forces were locked in a cosmic tug-of-war. Gravity, relentlessly pulling matter together, tried to collapse these regions into denser clumps. But the intense radiation pressure, pushing outward with tremendous force, resisted this collapse. This push and pull set the entire medium oscillating, creating vast, spherical sound waves that propagated outward at nearly 2/3 the speed of light. These were not sound waves as we hear them, but rhythmic compressions and rarefactions of the cosmic fluid itself, a booming echo reverberating through creation. When the universe suddenly became transparent during recombination, this cosmic music was abruptly silenced. The moment the plasma cleared and light was set free, the waves were instantly frozen in place, their final positions imprinted forever as a specific pattern of hot and cold spots on the sky. This is the true nature of the CMB map, a photograph of the universe at the very instant the music stopped. When cosmologists analyze the power spectrum of this map, they are not just looking at a jumble of notes. They are reading a precise musical score. The spectrum shows a distinct series of peaks, like the resonant harmonics of a giant bell. The first and most prominent peak, corresponding to the most common size for these frozen waves, confirmed the flat geometry of the universe we discussed earlier. But the subsequent peaks hold even deeper secrets. The second peak is a direct measure of the Baryon density, the amount of ordinary atomic matter, the stuff that makes up stars, planets, and us. Its height tells us that this ordinary matter constitutes less than 5% of the total energy in the cosmos. The third peak is a crucial clue about dark matter. Dark matter, which does not interact with light, felt gravity's pull but was immune to the pushing force of radiation. This changed how the cosmic fluid sloshed, and the characteristics of the third peak reveal how much of this mysterious, invisible substance permeates the universe. So, every time we look at the splotchy pattern of the cosmic microwave background, we are not just seeing light. We are witnessing the fossilized crests and troughs of the very first sounds, a literal echo of creation that tells us the composition and destiny of everything. These frozen sound waves tell a story far stranger than we ever imagined. They reveal a universe dominated not by the stars and galaxies we see, but by two profound and invisible mysteries: dark matter and dark energy. The cosmic microwave background gives us our most precise accounting of the cosmos, a complete inventory of reality, and the numbers are astonishing. The ordinary atomic matter, the stuff that builds every planet, every star, and every one of us, accounts for a mere 5% of the total cosmic energy budget. The remaining 95% is composed of entities we cannot see and barely understand. The first of these is dark matter. We know it is there because of its immense gravitational pull. The specific pattern of the CMB's acoustic peaks, especially the characteristics of that third peak, acts like a cosmic scale. It reveals that dark matter makes up about 27% of the universe. This invisible substance provided the essential gravitational scaffolding for the cosmos. Because it does not interact with light or ordinary matter, it was not pushed around by the intense radiation pressure in the early universe. This allowed dark matter to clump together first, forming deep gravitational wells into which normal matter could later flow, seeding the very first galaxies. Without dark matter's patient, invisible pull, the slight ripples in the CMB would never have collapsed into the grand cosmic structures we see today. The final and most dominant component is dark energy. This mysterious force, making up a staggering 68% of the universe, is responsible for its accelerating expansion. The CMB does not measure dark energy directly, but it provides the foundational starting point. By giving us an exact picture of the universe's geometry, density, and composition in its infancy, the CMB allows us to chart the entire cosmic expansion history. When we combine this baby picture with observations of the modern universe, like distant supernova, a startling truth emerges. The expansion, which should have been slowing down due to gravity, is instead speeding up. Something is overpowering the collective gravity of everything, and we call that something dark energy. So this ancient light does more than just show us our origins. It hands us a complete, if bewildering, recipe for the cosmos. A recipe written in the language of gravity, and written in the sky for anyone with the patience to read its faint, cold glow. Yet this ancient, uniform glow presents one of the most profound puzzles in all of cosmology. If you look at the cosmic microwave background in one direction, and then turn to look in the exact opposite direction, the temperature is virtually identical. These two regions of the sky are separated by a staggering distance, so vast that not even light, traveling for the entire age of the universe, could have had time to move between them. They were never in contact, so how could they possibly have reached the same temperature? This is the horizon problem. It is as if you walked into two separate, soundproof rooms on opposite sides of the planet and found two orchestras playing the same symphony, perfectly in sync, without any conductor or communication. For the early universe to be so perfectly uniform, some mysterious process must have coordinated its conditions everywhere at once. The leading solution is as breathtaking as the problem itself: cosmic inflation. This theory proposes that in the universe's first fleeting fraction of a second, it underwent a period of hyper-acceleration, expanding faster than the speed of light. Before this inflation, the entire patch of space that would become our observable universe was smaller than a single proton. At that tiny scale, it was a single, causally connected region, meaning energy and information could easily travel across it to smooth out all the temperatures, creating perfect uniformity. Then inflation struck. It took that tiny, uniform speck and stretched it in an instant to a size far larger than the entire cosmos we can see today. The regions that appear impossibly distant from each other in our sky were once intimately connected, nestled right next to each other in that primordial seed. This is why the cosmic microwave background looks the same in all directions. Its remarkable isotropy is not a mystery, but a direct prediction and a key piece of evidence for the inflationary paradigm. This realization carries a humbling implication. The entire universe we observe, with its hundreds of billions of galaxies, may be just a single, tiny patch, one small bubble in a frothing, possibly infinite, multiverse. The faint temperature ripples are only part of the story written in this ancient light. To see the full picture, we must also observe its polarization, a property that describes the specific direction in which the light waves are vibrating. This polarization is a fossilized record of the very last interactions those primordial photons had before they were set free. In the final moments before the universe became transparent, each photon scattered off a free electron for the last time. That final collision imprinted a specific polarization pattern onto the light, a subtle signature of the conditions in that searing plasma. We can think of this like sunlight glinting off the surface of a lake. The light becomes polarized, its waves aligning in a particular direction based on the angle of the reflection. In the early universe, the chaotic dance of electrons and photons created a similar but far more complex imprint across the entire sky. Scientists have mapped these patterns into two distinct families. The first are called E-modes. These are relatively simple, curl-free patterns, like the radiating lines of a spiderweb or the field around a positive or negative electric charge. They were generated by the same density fluctuations, the same sound waves, that created the hot and cold spots in the temperature map. They provide a different, confirming perspective on the distribution of ordinary matter. But it is the second type, the B modes, that hold the key to a far deeper mystery. These patterns have a curling, twisting quality, like the water swirling down a drain. While some B modes can be created by later effects like gravitational lensing, a specific, primordial type of B mode could only have been forged by one thing: gravitational waves from the universe's violent birth during inflation. Detecting this primordial B mode signal is one of the ultimate goals in modern cosmology. It would be a direct echo of the fabric of spacetime itself being violently rattled by the inflationary expansion, a literal tremor from the first instant of creation. Finding this faint swirl in the ancient light would not just confirm inflation. It would open a window to physics at energy scales 1 trillion times beyond what our most powerful particle colliders can ever reach, allowing us to listen to the very quantum vibrations of spacetime at the dawn of time. But the photon is not the only ancient traveler from the dawn of time. There is another, far more elusive background radiation filling the cosmos, a ghostly sea of particles that outnumbers even the photons of the cosmic microwave background. This is the cosmic neutrino background, a relic from the first full second after the Big Bang. Neutrinos are among the most enigmatic fundamental particles, often called ghosts because they carry no electric charge and interact with matter only through the feeble, weak nuclear force. A neutrino can pass through light years of solid lead without a single collision. This is why detecting these specific, primordial neutrinos directly is a monumental challenge that has yet to be achieved. We cannot simply point a telescope and see their glow. Yet, we are absolutely certain they are there. Trillions of them streaming through your body every second, completely unnoticed. Our proof comes from reading between the lines of the cosmic microwave background itself. These relic neutrinos, born just 1 second after the universe began, were a dominant component of the early cosmos. Their sheer numbers and their unique properties left a subtle but definitive fingerprint on the CMB we observe today. Because they are so light and fast, they streamed freely out of overdense regions in the early universe, effectively smoothing out the smallest clumps of matter. This suppression of structure on very small scales, combined with their contribution to the overall energy density of the young cosmos, imprinted a specific signature on the pattern of acoustic peaks in the CMB power spectrum. The data from missions like Planck match the theoretical predictions perfectly only when the presence of this cosmic neutrino background is included in the models. It is a ghost we see only by its shadow. A population of ancient particles we can prove exists by the precise way it shaped the first light. This indirect detection is a stunning triumph of cosmological theory, confirming that the universe is permeated by a second, even more ancient fossil, a cosmic backdrop of neutrinos that has been flowing through the void since the very first second of everything. This geometric truth about our cosmos is written in the size of the spots themselves. Across the modeled map of the cosmic microwave background, the most common hot and cold spots span approximately 1 degree of the sky. That specific angular size is not a random artifact. It functions as a cosmic standard ruler, a fixed measure imprinted by the physics of the early universe, allowing us to survey the largest possible geometry. To understand why this is so revealing, picture 2 parallel laser beams shot out into space. In a universe with positive curvature, a closed geometry resembling the surface of a sphere, those beams would slowly converge. In a universe with negative curvature, an open, saddle-shaped geometry, they would steadily diverge. Only in a perfectly flat universe would those 2 laser beams remain forever parallel. Now, translate that idea to the ancient light. The spots in the CMB were a fixed physical size when they were frozen in place. Their apparent size on our sky today depends entirely on how the fabric of space has curved the light's path on its long journey to us. The fact that we measure them at that precise 1 degree scale is the monumental discovery. It means that, on the grandest scales, the paths of those ancient photons were not bent. Our universe, as far as we can measure, is geometrically flat. This finding of a flat universe is one of the most profound in all of cosmology. It tells us that the average density of matter and energy in the cosmos is at a very specific, critical value. It suggests that the universe we can observe is most likely just a tiny patch of a much larger, and possibly infinite, reality stretching on forever. This single measurement, derived from the apparent size of frozen sound waves, forms the unshakable foundation of our standard model of cosmology, the lambda CDM model. It dictates the ultimate fate of our cosmos, pointing toward an endless, accelerating expansion into a cold, dark future. The entire destiny of everything was encoded in the dimensions of those first, faint ripples. Yet for all its precision, the cosmic blueprint holds a small but persistent anomaly, a single note that stubbornly refuses to fit the symphony. This is the cosmological lithium problem. According to our most detailed theories of Big Bang nucleosynthesis, the period in the first few minutes when the universe was hot and dense enough to forge the lightest elements, everything seemed perfect. The theory predicts with stunning accuracy the observed amounts of hydrogen and helium that fill the cosmos. These elements form the foundational fuel for the first stars and the basic building blocks of everything we see. But there is a glaring mismatch with the third lightest element, lithium. The calculations tell us we should find about 3 times more lithium-7 in the oldest stars of our galaxy than what our telescopes actually detect. These ancient stars are like cosmic time capsules, preserving the chemical composition of the early universe, and they all consistently show this lithium deficit. What makes this puzzle even more profound is the role of the cosmic microwave background. The CMB provides an exquisitely precise measurement of the Baryon density, the total amount of ordinary matter in the universe. This number is a crucial input for the nucleosynthesis calculations. When we plug this highly accurate value from the CMB into our models, the predictions for hydrogen and helium match exquisitely, but the prediction for lithium becomes even more stubbornly wrong. It is like having a perfect recipe where the amount of flour and sugar is confirmed by an independent lab, yet the cake consistently comes out with a mysterious ingredient missing. This tiny discrepancy is a major headache for cosmologists. It suggests that something is missing from our picture of the first few minutes. Perhaps there is an unknown form of particle physics at play, a relic particle from the early universe that interacted with neutrons or protons and altered the nuclear chain reaction that built lithium. Or maybe our understanding of how lithium is burned and destroyed inside the very oldest stars is fundamentally incomplete. This small crack in our otherwise triumphant model is a powerful reminder that the universe still holds mysteries, and that the ancient light, for all it reveals, still guards a few of its deepest secrets. Even as we map the frozen ripples of the ancient light, that light is still changing on its long journey to us. The cosmic microwave background photons have traveled for billions of years, and their path is not a simple flight through empty space. They have climbed out of and fallen into the gravitational wells of the vast cosmic structures that formed in their wake. This journey leaves one final, subtle mark upon them, a phenomenon known as the integrated Sachs-Wolfe effect. Imagine a photon of this ancient light approaching a massive cluster of galaxies. As it flies toward this immense concentration of mass, it must fight against the cluster's powerful gravity. In doing so, the photon loses energy, and since a photon's energy dictates its temperature, this loss causes it to appear slightly colder to us. Conversely, as the photon escapes from the far side of the cluster, it gains energy, appearing slightly warmer. In a universe completely dominated by matter, where the large-scale structures are relatively static, these two effects would perfectly cancel each other out. The energy lost on the way in would be exactly regained on the way out. But our universe is not static. Dark energy is causing the expansion to accelerate, and this acceleration is subtly changing the rules. The gravitational potentials, the hills and valleys of spacetime shaped by matter, are not permanent. As the universe expands at an ever-increasing rate, these massive cosmic structures are effectively being stretched and diluted. Their gravitational grip is weakening over time, so when a CMB photon falls into a potential well, it loses a certain amount of energy, but by the time it climbs out, The well has become shallower due to the dark energy-driven expansion. The photon does not get all of its energy back. There is a net gain, making the photon appear slightly hotter than the surrounding CMB in that direction. This creates a specific, predictable pattern on the largest scales of the CMB map. A faint correlation between hot spots and the locations of the most immense superclusters of galaxies. Detecting this signal is incredibly difficult, like listening for a single soft whisper in a roaring stadium. Yet, by cross-referencing exquisitely detailed maps of the cosmic microwave background with maps of the large-scale structure of the modern universe, astronomers have found it. This independent Sachs-Wolfe effect is now considered a direct, independent line of evidence for dark energy. It is not just telling us that the expansion is accelerating, it shows us dark energy in action, dynamically reshaping the gravitational landscape of the cosmos and leaving its signature on the oldest light of all. This faint afterglow does more than just tell us about the distant past. It also serves as a brilliant backlight for the universe's largest structures, a cosmic projector screen against which modern giants cast their shadows. When the ancient light passes through a massive galaxy cluster, it interacts with the superheated gas that fills the space between the galaxies. This gas is so incredibly hot that its electrons are moving at nearly the speed of light. As a cosmic microwave background photon journeys through this maelstrom, it can collide with one of these high-energy electrons. In a process known as inverse Compton scattering, the photon actually steals a tiny bit of energy from the electron. It gets a slight kick, boosting it to a slightly higher energy level. From our perspective, this creates a very specific and subtle distortion in the CMB map. At the precise location of the galaxy cluster, we see a tiny, telltale shadow, a slight dip in the CMB's intensity at its characteristic microwave wavelength, paired with a corresponding increase at shorter wavelengths. This is the Sunyaev-Zeldovich effect, a modern tool that turns the oldest light into a probe for the universe's grandest architecture. The true power of this effect lies in its independence from distance. For most objects in astronomy, the further away something is, the fainter it appears, but not for the SZ effect. The distortion it creates depends only on the density and temperature of the hot gas in the cluster, not on how far away that cluster is from us. This makes it an incredibly powerful finder for the most distant and massive clusters in the cosmos, the true behemoths that are otherwise almost impossible to spot. By conducting vast sky surveys to count these SZ shadows across different epochs, astronomers can trace the growth of cosmic structure throughout time. The number of massive clusters that formed at a given period in the universe's history is exquisitely sensitive to the underlying cosmological parameters, like the exact amounts of dark matter and dark energy. So, by using the cosmic microwave background as an immutable backlight, we can watch the silhouette of cosmic giants emerge and test the very laws that govern the expansion and fate of everything. The quest to decipher this ancient light is far from over. We stand at the threshold of a new era in cosmology, driven by colossal new observatories designed to listen to the universe's faintest whispers. The Simons Observatory, now under construction in Chile's high Atacama Desert, and the planned behemoth known as CMB Stage 4, represent a quantum leap in our technological reach. Their goals are nothing short of revolutionary. With arrays of thousands of supersensitive detectors, they will map the cosmic microwave background's polarization with a precision we can barely conceive of today. Their primary target is the holy grail of modern cosmology, the faint, swirling pattern of primordial B modes. Detecting this signal would be like finding the original fingerprint of cosmic inflation, a direct tremor from the universe's first fraction of a second. It would confirm that the cosmos underwent that phenomenal hyper-expansion and open a window into physics at energy scales 1 trillion times beyond the reach of any particle collider. But the mission does not end there. These observatories will scour the polarization maps for the ghostly signatures of new light particles that may have roamed the early cosmos, relics from theories beyond our standard model. They will act as cosmic historians, peering into the dark ages before the first stars ignited and tracing the distribution of dark matter with breathtaking clarity. Perched in the world's most extreme and arid environments, where the atmosphere is thin and stable, these telescopes are silent sentinels awaiting a message from the dawn of time. The data they will collect could fundamentally rewrite our understanding of creation, transforming the faint afterglow of the Big Bang from a snapshot of our past into a direct line to the very laws that birthed reality itself. Capturing this ancient whisper of creation is one of the most formidable challenges in modern science. The cosmic microwave background is astonishingly faint, a signal so weak it is easily drowned out by a cacophony of cosmic static. Our own Milky Way galaxy blazes brightly in the same microwave frequencies, its light a complex mix of emissions from spinning interstellar dust and electrons spiraling at near-light speed around magnetic fields. To isolate the pristine CMB signal, cosmologists must become master cleaners, meticulously scrubbing away this galactic foreground noise. The solution is to listen not with one ear, but with many. By observing the sky across many different frequencies, from radio waves to far infrared, scientists can fingerprint each type of interference. The galaxy's emissions have a distinct spectral signature, a specific way their brightness changes with wavelength, while the CMB has its own unique blackbody curve. It is a colossal effort in cosmic subtraction, using advanced algorithms to peel back these bright, local layers and reveal the subtle, uniform glow of the primordial universe beneath. But the interference does not stop at the edge of our galaxy. Our own atmosphere is a shimmering veil of water vapor that itself emits microwaves, creating a noisy, blurring screen between our telescopes and the cosmos. This is why the most powerful CMB observatories are built in the most extreme environments on Earth, on high mountain peaks in the Atacama Desert or at the South Pole, where the air is bone dry and staggeringly thin. For the ultimate clarity, we must go entirely beyond this atmospheric veil, launching missions like Planck into the pristine silence of space. The entire endeavor, from building these hypersensitive detectors in remote outposts to the years of painstaking data processing, is a monumental testament to human ingenuity. It is a silent, global collaboration of scientists working to hear a single, faint note played at the dawn of time, a note that has been traveling for 13 billion years just to reach our ears. Our universe appears to be perfectly tuned for our existence, a fact that has long puzzled scientists and philosophers alike. The fundamental constants of nature, the strength of gravity, the mass of an electron, all seem precisely calibrated to allow for the formation of galaxies, stars, planets, and ultimately, life. But what if this apparent fine-tuning is not a profound mystery of a unique cosmos, but simply a matter of our address? This is where the cosmic microwave background delivers its most mind-bending implication. The inflationary theory, so powerfully supported by the CMB's flatness and uniformity, suggests that our entire observable universe is just one bubble in an endless, frothing cosmic foam. If inflation is eternal, a process that started but never truly stopped, then it would continuously spawn new pocket universes, each inflating from the quantum fuzz of the greater multiverse. In this staggering picture, each of these bubbles could have its own unique set of physical laws and constants. Some might expand and collapse instantly, while others might be so empty and cold that no structure could ever form. We simply live in one of the rare bubbles where the numbers add up correctly for complexity to emerge. Our CMB, with its specific pattern of fluctuations and its precise flatness, is not a universal blueprint. It is a local weather report, the conditions of our particular cosmic neighborhood. This realization pushes cosmology to its very limits, blurring the line between science and philosophy. If a multiverse is real, can we ever have a final, complete theory that explains why our one universe is the way it is? Or are we merely cataloging the parochial bylaws of our own pocket reality, forever cut off from the grander laws that govern the whole? The ancient light we have worked so hard to decode may be our only fragile window into a reality so vast that our entire cosmos is just a single note in an infinite symphony. That faint glow is a literal window into the deep past. Observing the cosmic microwave background is the closest we will ever come to having a time machine. When our telescopes collect these ancient photons, we are not simply looking across vast stretches of space. We are gazing directly back across 13.8 billion years, witnessing the cosmos in its infancy. This is a unique form of cosmic archaeology. Every other object we study, from the planets in our solar system to the most distant galaxies, shows us the universe at a more developed stage, long after the first stars had blazed to life and sculpted the void. But the CMB is different. It captures a pristine moment before any of that existed. It is the universe before the first dawn, a silent, embryonic scene frozen in light. This allows us to probe the raw ingredients and initial conditions that would one day produce every galaxy, every star, and every planet. We are not just studying history, we are examining the original seed from which the entire cosmic tree grew. A single, timeless snapshot that holds the ultimate historical record of our reality. This ancient light connects the unimaginably large to the infinitesimally small. The extreme conditions of the newborn cosmos, revealed in the CMB's subtle patterns, serve as a unique laboratory for testing the most profound ideas in particle physics. We cannot build an accelerator powerful enough to recreate the searing energies of the universe's first moments, but we can use the cosmos itself as our experiment. The entire observable universe was once compressed into a volume smaller than a single atom, a domain where the fundamental forces of nature were likely unified into a single, super force. Theories like grand unification and supersymmetry, which attempt to describe this epoch, make specific predictions about the properties of the primordial seeds that would eventually grow into galaxies. These predictions are written into the statistical character of the hot and cold spots we observe. The simplest models of inflation suggest that the quantum jitters that seeded the cosmos should have produced fluctuations that are Gaussian. This is a statistical term meaning the distribution of these hot and cold spots should follow a very specific, bell curve-like pattern of randomness. There should be no hidden correlations or intricate twists connecting one fluctuation to another. It would be the cosmic equivalent of static, pure and simple. But what if our telescopes, with their ever-increasing precision, were to find a deviation from this perfect Gaussianity? Such a discovery would be a monumental clue, pointing toward more complex physics at play in the universe's first instant. It could be the signature of exotic particles, born in that fiery dawn, that interacted with the inflating field. Or it might reveal that the process of inflation itself was more intricate, involving multiple fields interacting in a cosmic dance. Finding even a hint of non-Gaussianity in the CMB's statistics would be like finding a fossilized whisper from the era of grand unification, a direct signal from when the forces of nature were one. This is the true power of the cosmic microwave background. It acts as a bridge connecting the quantum realm, which governs the behavior of particles, with the cosmic scale described by Einstein's theory of general relativity. These two pillars of modern physics have remained stubbornly separate, each magnificently successful in its own domain, yet refusing to be merged into a single, coherent theory of quantum gravity. The CMB gives us a single observational window that depends on both. The initial quantum fluctuations are magnified by inflation, a process rooted in general relativity's description of spacetime. By reading the detailed imprint left on the sky, We are essentially conducting an experiment that probes the intersection of these two great theories. We are asking the universe to show us how the tiny and the tremendous were woven together in the first moments of everything. This faint afterglow compels us to look inward as much as outward. That same ancient light bathing the earth touches every human being, a silent story written across the sky that predates every nation, every culture, and every story we have ever told about our origins. It is a universal heritage, a cosmic birth certificate we all share. This single, profound fact carries immense philosophical weight. The cosmic microwave background tells us unequivocally that the universe itself had a definitive beginning. It was not eternal and static, but emerged from a singular, fiery event and has been evolving ever since. We are not living in a fixed, unchanging arena, but are part of a grand, dynamic narrative that started nearly 14 billion years ago. And the scale it reveals is humbling. The observable universe contains hundreds of billions of galaxies, each with hundreds of billions of stars. Our entire world, our entire history, is contained on a tiny, fragile planet orbiting an average star in a quiet corner of one such galaxy. The CMB map makes this cosmic vastness tangible, forcing us to confront our true, minute physical scale in the grand scheme of things. Yet this realization is paired with a deep and intimate connection. Every atom in our bodies, the iron in our blood, the calcium in our bones, was forged in the hearts of long-dead stars. But the hydrogen, the most fundamental element of life, is older still. It dates back to the primordial universe, created in the first few minutes after the Big Bang. We are not just living in this universe, we are literally made of it, composed of ancient stardust and the primal hydrogen from the cosmic dawn. Perhaps the most staggering implication of all is that we can understand this. The human mind, through the language of mathematics and the power of careful observation, can decode the faint whisper of creation and reconstruct the history of the cosmos from its first moments. We can trace a direct line from the equations of Einstein to the pattern of hot and cold spots on a map of the entire sky. This is a profound testament to human curiosity and reason, a capacity to reach across time and space and ask fundamental questions about our own existence. The cosmic microwave background, therefore, is far more than a scientific dataset. It is a mirror. In its subtle patterns, we see reflected our own deep, enduring quest for meaning, our place in the cosmos, and our unyielding desire to understand where we came from. That lingering glow is not a distant wall in space, but a moment captured in time. One of the most common misconceptions about the cosmic microwave background is the idea that we are looking out at some kind of boundary, the edge of the universe where the expansion stops. This is not the case. The CMB is not a barrier in space, it is a surface in time. We are not looking at a faraway place, we are looking at a specific, ancient moment from our own location. Every direction we point our telescopes, we see this light because we are living inside the sphere from which it originated. Think of it like standing in the middle of a vast, foggy field. Suddenly, the fog lifts everywhere at the exact same instant. You can now see the entire field, but what you are actually seeing is the light that left every point on the field's surface at that single moment of clearing. You are not seeing the edge of the field, you are seeing a snapshot of the entire field taken at the time the fog vanished. We are at the center of our observable universe in exactly this way, seeing the light that finally reached us after a 13 billion-year journey from that universal moment of transparency. Another frequent misunderstanding involves the nature of the heat itself. It is tempting to call the CMB the leftover heat from the Big Bang explosion, but that is a slight oversimplification. The cosmic microwave background is not the heat of the initial fireball. It is the first light that was ever able to travel freely. For nearly 400,000 years, the universe was so dense and hot that light was trapped, constantly bouncing between particles. The CMB is the flash from that prison break. The glow released when the cosmos became transparent, and light could finally stream across the universe. This distinction is crucial because it frames the CMB not as a fading ember, but as an active, dynamic messenger. It carries a pristine record of the universe's state at that pivotal threshold, not from the very first instant, but from the moment it first opened its eyes. By clarifying these subtle but profound points, we transform the CMB from an abstract scientific concept into a tangible, and even more wondrous, piece of our history. It is not a distant, cold edge. It is the universe's own baby picture, and we are all living inside the album. That same modeled map of primordial hot and cold spots has escaped the confines of scientific journals to become a symbol etched into our collective consciousness. You have likely seen its distinctive, speckled pattern of red and blue, a celestial leopard skin, appearing in the background of science fiction films, on book covers, and even in modern art installations. It has become the definitive visual shorthand for the Big Bang, a single image that encapsulates humanity's deepest probe into the past. This is not merely a scientific diagram, it is a cultural artifact. It bridges the vast gap between the abstract mathematics of cosmology and the public imagination, transforming an incomprehensibly ancient event into something we can literally see and point to. The image makes the universe's fiery birth tangible, giving a face to the void and a story to the silence. When an artist uses this map in a painting or a filmmaker projects it behind a scene of cosmic wonder, they are tapping into a shared story of origin. It reminds us that the relentless pursuit of fundamental knowledge, of asking where we come from, is not a cold, detached exercise. It is a profoundly human endeavor, driven by the same curiosity that inspires poetry, music, and art. The cosmic microwave background has transcended its data-set origins to become a universal icon of exploration, a quiet testament to our species' unyielding desire to map the unknown, both outside in the cosmos and within the landscape of our own minds. This hunt for the primordial B-mode polarization is a search for the first tremors of spacetime. We are trying to detect the faintest possible curl in the ancient light, a specific swirling pattern that could only have been imprinted by gravitational waves from the universe's violent inflationary birth. These are not the gravitational waves we detect today from colliding black holes. Those are recent ripples in the cosmic pond. The waves we seek are the very first undulations, the primordial vibrations of spacetime itself, stretched to cosmological proportions during that first explosive moment of inflation. Finding their signature in the CMB would be like finding the fossilized echo of creation's first shudder. It would be the ultimate smoking gun, providing direct, incontrovertible evidence that inflation truly happened and allowing us to peer back into the Planck epoch. This is a realm where the energy was so immense that gravity itself was thought to be a quantum force, a domain forever beyond the reach of any particle accelerator we could ever build on Earth. The initial excitement from the BICEP-2 experiment in 2014, which claimed a detection, sent shockwaves through the scientific community. That announcement felt like a paradigm shift happening in real time. But the thrill was tempered by caution, and further analysis revealed that the signal they detected could be entirely explained by interstellar dust within our own Milky Way galaxy. It was a sobering reminder of the immense challenge of this search, of separating an impossibly faint cosmic signal from a cacophony of local interference. Yet the hunt has only intensified. The retraction was not an end, but a new beginning, fueling a global race with ever more sophisticated telescopes, like the Simons Observatory, being built in the world's driest deserts to listen for this whisper with unparalleled clarity. To finally capture this signal would be to touch the quantum origins of gravity itself. It would be a discovery worthy of the highest scientific honors, not for the prize itself, but for what it would confirm, that our most ambitious theories about the beginning of everything are written in the sky, waiting in the silent polarization of the oldest light. The cosmic microwave background is far more than a cold remnant of a hot beginning. It is a dynamic and living source of information, a celestial archive that continues to redefine our place in the cosmos. This ancient light began as a triumphant confirmation of the Big Bang, a discovery born from stubborn static in a New Jersey antenna. It then revealed the seeds of all structure, the frozen symphony of sound waves that gave rise to galaxies. It handed us the complete recipe for reality, showing us a universe dominated by dark matter and dark energy. And now, it pushes our imagination to the very edge of physics, hinting at a multiverse of bubbling cosmic domains. This faint glow is our most direct, unbroken link to the origin of everything. As our technology advances with observatories of staggering sensitivity, we will not just find answers to our current questions. We will peer deeper into its subtle polarizations and statistical whispers, and we will discover new mysteries, learning to ask questions we have not yet even conceived. Let this journey remind you that the night sky is not a distant, silent curtain. It is a living storybook, and its faintest, most pervasive glow holds the entire narrative of our cosmic home, from the first quantum tremor to the vast, accelerating present. We would love to hear what part of this cosmic mystery resonates most with you. Share your thoughts and wonder in the comments below.